Ming Feng is with CSIRO. I don't think Ming needs any introduction. He's going to talk about that large domain in the realm of climate change.
Okay, thank you, Stuart. So I was trained as a observational oceanographer. Thank WAMSI for recruiting me as a modeler. So I think it's very hard to squeeze the work from the whole project into a 10-15 minutes kind of talk. So I kind of focus on one topic, the marine heatwaves, which causing the coral bleaching of the Kimberley coast. So the topic would be the opposite polarities of ENSO drive distinct patterns of coral bleaching of a WA coast. The acknowledged page is at the end of the talk. Okay, this is a diagram that Matt shows, showed before. So basically, I add this column here, IPCC models. To look at the climate change, you have to understand what IPCC has produced so far. So the model domain we work with is to understand the IPCC modeling research result, and we use an OFAM model, which has a 10-kilometer kind of resolution. It's a near global model to look at the Australian-wide kind of issues of ocean circulation. And then we use a ROMS model that Matt just introduced to downscale the OFAM result to the regional scale. So that's kind of the hierarchy we are looking at. So the focus will be on the hydrodynamics. So to write this down. Yep. So okay, so basically modeling are tools for us. So we look at the different scales, the IPCC modeling scales. We have an ocean grid of 100 kilometers, as we will see it in later. So it's good to look at the basin scale patterns, and maybe it's a climate mode. For example, whether El Nino, La Nina will change in the future climate. So that's the purpose of that kind of model. I think for OFAM model, or somebody called a blue link model, we have a 10-kilometer resolution. We start to resolve the ocean boundary current and some of the shelf processes, like the Capes current, some of the coastal upwelling, for example. And if we're moving down to regional model, like the ROMS that map the top, we have 1 to 2 kilometer kind of resolution. So we start to resolve some of the coastal processes. We can have the tides kind of signal, and we can look at the probably more relevant to the marine park management. I mean, we know that people manage the marine park at that kind of a spatial scale. So, okay, so first of all, we look at the IPCC model simulation. So we know that IPCC has devised a few kind of CO2 emission scenarios. There's probably a few, 8.5 is the highest one, RCP 6, they call it representative concentration pathway. So RCP 4.5 is a middle range, and 2.6 is more on the lower range. So on the lower panel is showed some of the IPCC model result. On the high end, so 8.5 kind of scenario. So the reason showing that is we want to alarm the decision makers that if you don't do anything now, this will likely occur in the future. So we hope, I mean, by showing this, we will bring the CO2 emission downward, and in the future, we will actually follow these kind of lower emission scenarios. But still, from this picture, I mean, we can see a few kind of information, signals. One is, in the future climate, the land will warm faster than the ocean. So that's kind of one conclusion from probably the large-scale model. So you can see Australia probably continent will warm probably 4 to 5 degrees in the toward the end of the century. So also, I mean, the other signal is that northern hemisphere is warming faster than the southern one. This means it's a landmass distribution. I mean, in the northern hemisphere, there's more landmass, and the other conclusion would be in the polar region, there's kind of the fastest kind of warming trend, which will melt the ice and causing the sea level rise. So that's kind of a large scale kind of picture. So you can see that from this model, we don't resolve the Kimberley coast or the ocean boundary current around Australia at all. So for example, the lunar current is only probably less than a grid point in this kind of model. So we need this kind of regional model to be able to resolve the ocean boundary current and to look at the issues that are more relevant to us. So this is one model that we did in collaboration with a whole bunch of people in Hobart. we use an OFAM model, it's a 10 kilometer resolution near global model, to use the RPCC model as a forcing to drive this model for 100 years into the future. So we want to understand how these ocean boundary conditions, ocean boundary currents, like the EAC, lower current in the Newton through flow will change in the next kind of 100 years. So we published a few papers. So I think we have one paper published last year. We're talking about the energizing ocean boundary current system around Australia during this period, 1979 to 2014. I think we have heard that that period is the so-called climate change highest period. So during that period, all the ocean boundary current and their eddies are becoming stronger. So during the highest period. But I don't have time to show other results. But when you do the 100-year simulation, that's the real climate change signal. The RTF, the through flow, and the lower current will become weaker. So that's a long-term trend. But during the climate hiatus, things will kind of reverse. Okay, so I think, I didn't bring the picture showing the Rowley model result. I think Matt has shown that already. So basically, when we have this kind of model, we will be able to resolve the boundary current, the seasonal reversal of the boundary current. Like in winter, we have the Rowley current, and in summer, we have the monsoon, wind-driven current, so etc. So, okay. So move back to my topic. So we know that during 2016, we observed probably the worst kind of coral bleaching of the Kimberley coast, especially probably at Scott Reef. There are a few people from AIMS working on that intensively. There are 60% kind of coral bleaching at Scott Reef and 10% or more in Rowley Shoals. And this is caused by this kind of warming signal occupying the whole kind of northern Australia kind of region. This is the temperature anomaly. So for the whole region, during the summer period between 2015 to 16, the whole area is warmed by more than 1 degree. The peak temperatures are a little bit higher than that. So I think if you look at that, so from Pilbara down south, actually we see some cooling signal. So when this region is warmed up, this region is actually cooling down. And we know that that year was an El Nino year. So I think we want to use modeling to understand that why is that. So here's a quick kind of notes. I mean, we know that that year is El Nino year. So this is the index of El Nino La Nina. I mean, when it's positive, it's El Nino, and when it's negative, it's La Nina. So 2015-16 is a very strong kind of El Nino event, and we have the warming in the north and cooling down south. And we know that a similar kind of coral bleaching event occurred in 1998, which was also an El Nino event. And in 1982-83, there was another strong El Nino, which we didn't record any coral bleaching, which means probably there's a long-term trend as well. On the opposite, during La Nina event, so which is a negative, the index, we see there are quite a few events as well. And we found that in 2011 and 12, we observed very strong kind of warming and coral bleaching of the west coast from Ningaloo to Abroad and all the way to Rottnest Island. So I think during the peak of that event, we found that there's a little bit kind of cooling in the north. So there's a kind of during the opposite kind of polarities of El Nino, we have observed different patterns of coral bleaching potential or warming patterns. El Nino, we have warming and coral bleaching in the north, and the La Nina, we have warming and coral bleaching in the south. So, okay, so this is a kind of, when we do a composite, we select probably 6 El Nino events and 6 La Nina events. I think here I only show the El Nino events. So there's a kind of transition between a little bit of kind of cooling trend between September, October, November in the kind of a winter to spring kind of period to a very kind of a strong kind of warming of the northern Australia region in December, January, February in the following year. So that's a transition. I think that's a paper we published recently. I mean, in the scientific report, people have interest would have a read. So why is that? So we look at the forcing field. We know that probably during the spring to summer, we have this kind of monsoon, Australian monsoon onset. So this is a normal condition in December, January, February. You can see the monsoon winds is eastward here. And during that summer, or during the El Nino summer, I would say, the wind anomaly is toward the west, which reduces the total wind speed. So, and also during El Nino summer, the red indicating that in the region there's less cloud. So all the cloud moved eastward with the El Nino warming in the equatorial Pacific. So there are two signals here. One is less cloud, so you allow more solar radiation penetrating into the ocean, warm the ocean surface layer. The other is the wind is weakening, so you have a less strong kind of Australian monsoon, which means there's less evaporation from the ocean to the atmosphere. We know evaporation cools the upper ocean. So the combination of these two factors drive this kind of warming condition in the Austral summer during El Nino year, and it causes the transition from a relatively kind of cool condition during the autumn into a very strong kind of warming in the summer season. So yeah, we use the OFAM model to confirm that. So I won't go into any details. Basically, we use a very simple model. So this is your warming temperature trend, dt. I mean, if this is strong, you have strong warming, which is here I showed in two seasons. Yeah, in autumn and summer season. So dt is positive, which means it's warm up in El Nino years. And this is the air-sea heat flux. So the total air-sea heat flux, which include the solar radiation anomaly and evaporation anomaly. So we found that this kind of warming is totally caused by this air-sea heat flux in the region. And the residual term we didn't calculate is we called ocean advection, including the Lowland current. In fact, it's play a negative role. So, which means in the region, the warming during El Nino is totally driven by the air-sea heat flux due to the weakening of the monsoon and the reduction of the rainfall and the cloud in the region. So on the opposite, we know that the warming in the south is purely due to the Lowland current advection. We have some work with Nick the last kind of few years as well. So here's a summary, I guess. I mean, so I won't go into any details. So we devise an index we call it marine heatwave index. So which has a frequency, how long the marine heatwave lasts, how many days, and the cumulative intensity. It's very like the what's called a coral bleaching index that NOAA has devised. So what this is a summary plot showing that in the northern reef, from Christmas Island, Scott Reef, Ashmore, Kimberley coast, to Rowley Shoals as well. So we found that there's a more likelihood of longer, more frequent marine heat waves during El Nino event. And in the south area, so from Mount Bellow to Aberroles, La Nina will cause more likelihood of marine heat wave. So that's our kind of main result for this study. So now I move on to the long-term trend. And we know that the ocean temperature has been warming up over the past probably half decade. So this is a kind of Australia-wide kind of warming trend. We know Kimberley coast, it probably warmed fast in December kind of season over the past 50 years. So that would exaggerate, I mean, whatever the El Nino, La Nina kind of contribution to the warming in that region. This one thing, and another thing is when we run our OFAM model under the RCP 8.5 model simulation, we found that in the region, especially in the coastal region, there's a kind of 0.03 degree per year kind of warming trend, which translates to 3 degrees kind of warming over 100 years, for example, if we, which is a worst kind of scenario we have on the climate kind of change. And one thing probably I should kind of point out, I mean, we also use the ROS model, thanks Kenji Shimizu, who sits here still, I guess, somewhere. We did 2 simulations. One simulation on the current climate in the 2000s. The other is we did another simulation, a downscale from the OFAM model in the 2060s. So we can understand the climate change impact on this kilometer kind of a scale. So I think this data set is there, and the result hasn't been fully explored. I would only show one result here. So this is a transect from inshore of Kimberley coast to the open ocean region. So this is a mean kind of temperature distribution. So you can see surface is 30 degrees, and it's cooling. There's a thermal climb here, and probably, as Matt mentioned, in the nearshore area, it's not stratified. There's a strong kind of tidal mixing. But in the future climate, this is the future minus the present. You can see the surface layers warms much faster. So 2 degrees, probably 2 to 3 degrees in the surface layer. And the middle layer has a kind of slightly kind of cooling trend, probably due to the throughput kind of change. So there's an enhancement of stratification on the shelf. To what extent the coastal region will be affected? Now we will kind of further explore that. So here's the summary. So we need a hierarchy kind of modeling approach to tackle the climate change. We need to understand how RPCC model perform. And we need to use a global model to downscale that. And we need to use a local model to look at our local kind of marine park issues. And we look at the El Nino, how El Nino drives this kind of marine heatwave event by reducing the cloud cover and weaken the Australian monsoon. And we know that in the future climate, we have fast increasing trend of temperature, which increases the stratification and may affect other biological kind of activities in the region. So, okay, I'll stop here, and here's my acknowledgement. Thank you.